Most of the time, space feels solid in its reliability. There's always a little more distance ahead, a little more time passing by. Rooms have corners, paths have length, moments follow one another in a steady, familiar order. Physics for centuries agreed with this intuition. Space could be divided again and again. Time could be sliced into ever smaller moments. Reality, it seemed, was smooth all the way down. But as measurements grew sharper, something subtle began to happen. At very small scales, the rules that govern atoms and particles refused to cooperate with the geometry of spacetime itself. The tools that describe gravity stop working cleanly. Distance becomes harder to define. Time loses its steady rhythm, and the idea of a smooth, continuous universe begins to look less like a fundamental truth and more like a remarkably good approximation. Somewhere far beyond everyday experience, spacetime may no longer behave as a stage on which events unfold. It may fluctuate, it may fragment, or it may emerge only when viewed from far enough away, like the smooth surface of the ocean hiding restless motion beneath. This raises a quiet but profound question. Not where spacetime becomes strange, but when. At what point does space itself stop being classical and start behaving like a quantum object? Welcome to The Sleepy Scientist. If you enjoy calm, thoughtful science like this, please like the video and subscribe to the channel, and let me know in the comments where you're watching or listening from, whether you're grounded in one familiar place or drifting quietly through space and time somewhere else. Space and time usually present themselves as stable and continuous features of experience. A room extends smoothly from one wall to another. A path connects two places without interruption. A moment gives way to the next in an orderly sequence. There is no sense that distance comes in pieces or that time advances in steps. Everything appears divisible without limit. This impression is not subtle. It is reinforced constantly by movement, measurement, and memory. A table can be measured in meters, then centimeters, then millimeters. With better tools, the same surface can be resolved into smaller and smaller lengths. No matter how closely it is examined, a space appears to allow further subdivision. Time behaves the same way. A minute can be divided into seconds, seconds into smaller intervals, and those intervals into still finer ones. The process never seems to reach a boundary. Because this behavior aligns so closely with experience, it shaped the earliest formal descriptions of the physical world. Classical geometry treated space as continuous by definition. A line had length but no thickness. A point had position but no size. Between any 2 points, another point could always be placed. These ideas were not experimental conclusions but mathematical foundations. Geometry assumed continuity because it was consistent, powerful, and matched observation. When physics began to formalize motion and force, it adopted the same assumptions. In the late 17th century, Isaac Newton described space as absolute. Space existed independently of matter and provided a fixed arena in which objects moved. Time was also absolute, flowing uniformly and identically everywhere. Events unfolded within this framework, but did not alter it. Newton's laws of motion rely on this picture. Position, velocity, and acceleration are defined using continuous space and continuous time. A body moves along a path that can be specified precisely at every moment. Forces act continuously, producing smooth changes in motion. The mathematics presumes that positions and moments can be specified with arbitrary accuracy, at least in principle. This framework proved extraordinarily effective. At human scales, classical mechanics predicts motion with reliability that borders on routine. Bridges remain standing because stresses can be calculated accurately. Vehicles move as expected because forces and trajectories behave predictably. The assumptions of smooth space and time introduce no detectable error in these contexts. The same is true far beyond everyday experience. Planetary orbits described using Newtonian gravity can be predicted centuries into the future. The positions of planets, moons, and comets follow paths that are smooth, continuous, and stable over long periods. Even before modern instruments, astronomers could calculate eclipses and alignments with impressive precision. Distances on astronomical scales reinforce the same conclusion. The average distance between Earth and the Sun is about 150 million kilometers. The nearest star beyond the Sun is more than 4 light-years away, roughly 40 trillion kilometers. These immense separations behave exactly as a continuous spatial framework would suggest. Light travels predictable paths. Objects move along smooth trajectories. No irregular structure in space interferes with these motions. Timekeeping offers a similar picture. Modern atomic clocks measure time using the oscillations of atoms, achieving precision such that they lose less than 1 second over millions of years. These clocks rely on quantum processes within atoms, yet the time they measure behaves as a continuous quantity. There is no evidence at these scales that time itself advances in discrete jumps. Even when gravity was reconceived in the early 20th century, continuity remained intact. Albert Einstein's theory of general relativity replaced Newton's absolute space and time with spacetime, a unified structure combining 3 dimensions of space with 1 of time. In this description, gravity is not a force acting through space but a manifestation of curved spacetime produced by mass and energy. Despite this conceptual shift, spacetime in general relativity remains smooth. The theory assumes that spacetime can be described by continuous geometry at every scale. Curvature may become extreme near massive objects, but it is still defined at every point. The equations describe how spacetime bends, stretches, and evolves without requiring any smallest unit of length or time. This assumption has been tested extensively. General relativity predicts the bending of light near massive objects, the precise precession of planetary orbits, the slowing of time in gravitational fields, and the existence of gravitational waves. Observations from radio telescopes, spacecraft, and detectors such as the Laser Interferometer, Gravitational Wave Observatory, often referred to as LIGO, confirm these predictions with high accuracy. Across this vast range of scales, from laboratory experiments to cosmic distances, spacetime behaves as though it is smooth and continuous. This consistency is not accidental. It reflects the fact that the underlying assumptions align well with the dominant physical processes at these scales. One reason smoothness works so well is that most measurements involve large numbers of underlying interactions. Any microscopic irregularities are averaged out. Just as a solid table appears continuous despite being made of atoms separated by empty space, spacetime may appear smooth because its fine structure, if it exists, is far smaller than the scales being probed. This idea is common in physics. Temperature feels like a continuous quantity, rising and falling smoothly. In reality, it reflects the average kinetic energy of many particles. At the level of individual atoms, energy changes occur in discrete interactions, yet the aggregate behavior is well described by continuous variables. Fluid motion offers another example. Water flowing in a river obeys equations that treat it as a continuous medium. These equations succeed because they describe behavior at scales much larger than individual molecules. At sufficiently small scales, the description fails, but only because it is being applied outside its domain of validity. Smooth spacetime may function in the same way. It may be an effective description that captures large-scale behavior while remaining silent about finer structure. The absence of observable irregularities does not guarantee that none exist. It indicates only that they do not matter for the phenomena being described. Importantly, nothing in ordinary experience forces this question into view. There are no visible gaps in space. There are no missing moments in time. Motion proceeds continuously, and measurement refines smoothly. This is precisely why classical and relativistic descriptions have endured. They describe the world as it presents itself across an enormous range of conditions. However, physics does not stop at familiar scales. As investigations pushed towards smaller distances and higher energies, new behavior emerged. Matter no longer followed smooth trajectories. Energy appeared in discrete amounts. Measurements acquired fundamental limits. Quantum mechanics revealed that continuity, so successful at large scales, was not a universal feature of physical law. The recognition that matter behaves differently at small scales raises a natural question. If particles and fields obey quantum rules, what about the spacetime they inhabit? Does spacetime remain continuous no matter how closely it is examined, or does its apparent smoothness reflect the limits of observation? The classical picture remains essential. It captures real, measurable behavior with remarkable accuracy. Any deeper description must recover this smoothness where it applies. The goal is not to discard the familiar framework, but to understand why it works so well, and where it might stop being the whole story. The idea that space and time might be more than a passive setting marks one of the most important shifts in the history of physics. This shift is closely associated with Albert Einstein, who in the early 20th century proposed a radically different way of understanding gravity and motion. Before this change, gravity was treated as a force acting between masses across space. Objects attracted one another, and the strength of that attraction depended on their masses and separation. Space itself played no active role. It simply existed, providing distances over which forces acted and time during which motion unfolded. Einstein approached the problem from a different angle. Instead of asking how objects move through space under the influence of gravity, he asked what space and time themselves are doing in the presence of matter and energy. The result was the theory of general relativity, published in 1915. At its core is a simple but far-reaching idea. Gravity is not a force in the traditional sense. It is a geometric effect. Mass and energy change the structure of space-time, and objects move in response to that structure. In this view, space-time is not an abstract backdrop. It is a physical entity with properties that can change. To understand this, it helps to separate intuition from formal mathematics. General relativity is often associated with complex equations, but the central concept can be described without them. Space-time can curve. That curvature influences how objects move. An object that is not being pushed or pulled follows the straightest possible path through space-time. In flat space-time, that path looks like uniform motion in a straight line. In curved space-time, the same principle applies, but the path itself is bent because the geometry is bent. This is why gravity can be understood without invoking a force. A planet orbiting a star is not being tugged along a curved path by an invisible pull. Instead, it is following the natural geometry of space-time shaped by the star's mass. The orbit appears curved because space-time is curved. A common analogy involves a stretched surface with a heavy object placed at its center. Smaller objects placed nearby roll inward, not because they are pulled sideways, but because the surface beneath them slopes. While this picture has limitations, it captures the essential idea. Geometry directs motion. In Einstein's theory, mass and energy determine how spacetime curves. This relationship is precise and quantitative, even though it can be described qualitatively. Dense objects such as stars and planets create stronger curvature than less massive ones. Extremely compact objects, such as neutron stars and black holes, produce curvature so intense that it dramatically alters the behavior of space and time around them. Importantly, energy also plays a role. Pressure, momentum, and energy density all contribute to spacetime curvature. Light itself, despite having no rest mass, follows curved paths in the presence of massive objects because spacetime is curved, not because light experiences a force. This leads to one of the earliest and most famous confirmations of general relativity: gravitational lensing. In 1919, during a solar eclipse, astronomers observed that the apparent positions of stars near the Sun were slightly shifted. The starlight had passed close to the Sun on its way to Earth, and its path had been bent by the curvature of space-time around the Sun. This effect was small but measurable, and it matched Einstein's predictions. Gravitational lensing has since become a standard observational tool in astronomy. Massive objects such as galaxies and clusters of galaxies bend light from more distant sources, producing arcs, rings, and multiple images. These observations confirm that space-time curvature is not a mathematical abstraction. It has direct, observable consequences. Time is also affected by curvature. In general relativity, clocks run at different rates depending on their position in a gravitational field. A clock closer to a massive object ticks more slowly than one farther away. This phenomenon, known as gravitational time dilation, has been confirmed through experiments involving atomic clocks placed at different altitudes. Even systems as familiar as global positioning satellites must account for this effect. The clocks aboard these satellites experience both special relativistic time dilation due to their speed and gravitational time dilation due to their distance from Earth. Without correcting for these effects, navigation errors would accumulate rapidly. These confirmations establish spacetime as an active participant in physical processes. It stretches, bends, and influences motion. It is not merely where events happen, it helps determine how events unfold. Despite this dynamic role, spacetime in general relativity remains smooth and continuous. Curvature changes gradually from point to point. Distances and durations can still be subdivided without limit. There is no smallest length built into the theory. Spacetime behaves like a flexible but continuous fabric. This smoothness is essential to how general relativity works. The mathematics assumes that spacetime has well-defined properties at every location. Curvature is described locally, meaning that it can be specified in arbitrarily small regions. The theory relies on the idea that spacetime can be examined at finer and finer scales without losing meaning. At the scales where general relativity has been tested, this assumption holds extremely well. From the bending of light near stars to the dynamics of galaxies, spacetime behaves as a smooth geometric structure. Even the detection of gravitational waves, ripples in spacetime produced by accelerating masses, confirms this picture. These waves propagate smoothly across vast distances, stretching and compressing space by tiny amounts as they pass. The success of general relativity reinforces the idea introduced earlier. Smooth spacetime is not a naive guess. It is a carefully tested description that works across a remarkable range of conditions. At the same time, the theory contains hints that its domain of validity may be limited. Certain solutions to Einstein's equations involve singularities, points where curvature becomes infinite and the mathematical description breaks down. The centers of black holes are the most well-known examples. These singularities are not directly observable, but their presence suggests that general relativity is being pushed beyond where its assumptions apply. Infinite curvature is not a physical prediction so much as a signal that the theory has reached its limits. Crucially, these problematic regions arise when matter and energy are compressed into extremely small volumes. In other words, they occur at scales far removed from everyday experience. This raises the possibility that spacetime behaves differently under such extreme conditions. Still, it is important to emphasize what general relativity gets right. It provides a coherent, predictive framework in which spacetime is both smooth and dynamic. It explains gravity without invoking forces acting through empty space. It unifies space and time into a single structure that responds to matter and energy. This view deepens the idea of smooth spacetime rather than undermining it. Space and time are not just continuous, they are structured. They have geometry. They participate in the physical world. Any deeper theory of spacetime must recover this behavior where it has been tested. Smooth geometry is not an illusion to be discarded. It is an accurate description within its range of applicability. Understanding spacetime as geometry sets the stage for more challenging questions. If spacetime can bend and evolve, if it carries energy and supports waves, then it begins to resemble other physical systems that are known to have underlying microscopic structure. The question that follows is not whether spacetime is real or effective, it is whether the smooth geometric picture remains valid at all scales, or whether, under sufficient scrutiny, spacetime itself must be described using different principles. For now, what matters is this. General relativity transforms spacetime from a silent backdrop into an active, measurable entity. It behaves smoothly, continuously, and predictably across the universe we observe. That success must be understood before any attempt is made to go beyond it. General relativity is one of the most successful theories ever developed in physics. Its predictions have been tested repeatedly across many decades, and in environments ranging from laboratories on Earth to the edges of the observable universe. Wherever it has been applied within its expected range, it has performed with remarkable precision. At large scales, the theory describes gravity as the curvature of spacetime produced by mass and energy. This description accounts for the motion of planets, the structure of galaxies, and the expansion of the universe itself. Observations of planetary orbits, binary star systems, and galactic dynamics all align closely with the predictions of Einstein's equations. One of the clearest demonstrations of this success comes from gravitational waves. These waves are ripples in spacetime generated by accelerating masses, particularly during violent cosmic events. In recent years, detectors such as LIGO have observed gravitational waves produced by merging black holes and neutron stars. The signals detected match the waveforms predicted by general relativity with striking accuracy. The timing, amplitude, and decay of these signals provide strong evidence that spacetime behaves exactly as the theory describes, even under extreme conditions. General relativity also performs exceptionally well in environments involving strong gravitational fields. Neutron stars, for example, are among the densest objects in the universe. A typical neutron star contains more mass than the Sun compressed into a sphere roughly 20 kilometers across. The gravitational field at its surface is billions of times stronger than Earth's. Despite this, general relativity successfully describes the structure, stability, and gravitational influence of these objects. Black holes provide an even more extreme test. These objects form when massive stars collapse under their own gravity, compressing matter to such a degree that not even light can escape from within a certain boundary known as the event horizon. The existence of black holes was once a theoretical possibility, but it is now supported by multiple lines of evidence, including stellar motions near galactic centers, high-energy radiation from accretion disks, and direct imaging of black hole shadows. The mathematical description of black holes within general relativity traces back to Carl Schwarzschild, who, in 1916, discovered an exact solution to Einstein's equations describing the spacetime around a spherical non-rotating mass. This solution revealed the presence of an event horizon, and deeper still, a singularity at the center. At the event horizon, spacetime curvature becomes extremely strong but remains finite. An observer falling through this boundary would not experience anything locally unusual at the horizon itself. From their perspective, physics continues smoothly, at least initially. From the perspective of a distant observer, however, time appears to slow dramatically near the horizon. These effects have been confirmed indirectly through observations of matter spiraling into black holes and through gravitational wave signals from black hole mergers. Up to this point, general relativity remains internally consistent and observationally successful. Problems arise only when attention turns to the singularity itself. A singularity is a region where quantities such as spacetime curvature become infinite. In the Schwarzschild solution, the singularity lies at the center of the black hole, where the equations predict that density and curvature diverge without bound. Similar singularities appear in models of the early universe, where extrapolating the equations backward leads to a point of infinite density, often associated with the beginning of cosmic expansion. These infinities are not merely large numbers, they indicate a breakdown of the mathematical framework. Physical quantities lose their meaning, distances shrink to zero, time ceases to behave in a well-defined way. The theory no longer provides sensible predictions. Importantly, singularities are not considered physical objects in the same way planets or stars are. They are better understood as warning signs. They indicate that the assumptions underlying the theory are being pushed beyond where they apply. In particular, they signal that treating spacetime as a smooth, continuous geometry may no longer be valid under such extreme conditions. This distinction matters. General relativity does not fail gradually as conditions become more extreme. It remains accurate up to the edge of these singular regions. Only when curvature and density reach extraordinary levels does the description collapse. This suggests that the theory is not wrong but incomplete. The incompleteness becomes clearer when quantum effects are considered. Neutron stars and black holes involve matter compressed into very small volumes. At sufficiently high densities, the quantum properties of matter cannot be ignored. Electrons, neutrons, and other particles obey quantum rules that limit how closely they can be packed. These quantum effects are essential to preventing many stars from collapsing further, as in the case of neutron degeneracy pressure. General relativity, however, treats matter in a largely classical way. It does not include the quantum behavior of particles at a fundamental level. This omission is not problematic at low densities or large scales, but it becomes critical when matter is compressed into extreme states. The same issue applies to spacetime itself. General relativity assumes that spacetime can be described as a smooth continuum down to arbitrarily small scales. Quantum mechanics, by contrast, introduces fundamental limits on measurement and precision. When energy is confined to very small regions, quantum fluctuations become significant. Attempting to probe spacetime at extremely small distances requires high energies, which in turn strongly disturb the spacetime being measured. This tension suggests that singularities arise not because spacetime truly becomes infinite or ill-defined, but because the theory describing it is being used outside its domain of validity. The smooth geometric picture works exceptionally well until it encounters regimes where quantum effects cannot be ignored. Evidence for this limitation also appears in cosmology. When the equations of general relativity are applied to the universe as a whole, they describe an expanding spacetime that was denser and hotter in the past. Extrapolating this expansion backward leads to a state of extremely high density and temperature. Eventually, the equations predict a singular beginning. Yet this extrapolation assumes that classical spacetime remains valid all the way back. At early times, when the universe was extremely small and energetic, quantum effects would have been unavoidable. The appearance of a singularity in this context again suggests a boundary beyond which the classical description breaks down. It is worth emphasizing that these issues do not undermine the successes of general relativity. The theory remains the best available description of gravity and spacetime at macroscopic scales. Its predictions continue to be confirmed with increasing precision. The problems arise only when the theory is extended into regimes it was never designed to handle. In this sense, singularities serve a constructive role. They highlight the points at which new physics is required. They indicate where a more complete framework must take over, one that incorporates both the geometric insights of general relativity and the probabilistic structure of quantum mechanics. The existence of these limits motivates the search for a deeper theory. Not because general relativity fails broadly, but because it succeeds so completely within a well-defined range. Understanding where and why it stops working provides clues about the underlying structure of spacetime itself. The picture that emerges is one of layered description. Smooth spacetime geometry governs the large-scale behavior of the universe. It explains gravity, motion, and cosmic structure with high accuracy. But at extreme densities and small scales, the assumptions that support this picture may no longer hold. Recognizing both the success and the limits of general relativity sets the stage for the next step. If smooth spacetime breaks down only under the most extreme conditions, then the question becomes precise rather than speculative. At what scale do those conditions arise, and what replaces the classical description when they do? The cracks in smooth spacetime do not appear everywhere. They appear only where nature is pushed to its extremes. That fact narrows the problem and gives it direction. As the limits of classical spacetime become visible under extreme conditions, a very different framework enters the picture. This framework was not developed to explain gravity or cosmic structure, but to understand how nature behaves at very small scales. It is known as quantum mechanics, and it describes a world that does not behave smoothly or continuously in the way classical physics assumes. Quantum mechanics emerged at the beginning of the 20th century, not from philosophical speculation, but from experimental failure. Classical physics could not explain how atoms emit light, how energy is exchanged, or why matter remains stable. Predictions disagreed with observations in precise and repeatable ways. Something fundamental was missing. One of the first clear signs appeared in the study of heat and radiation. When physicists examined how hot objects emit light, classical theory predicted that energy should be released continuously across all frequencies. This prediction led to results that did not match reality and, in some cases, implied infinite energy output. The problem was not subtle. The equations simply did not work. In 1900, Max Planck proposed a radical solution. He suggested that energy is not exchanged continuously, but in discrete amounts. These amounts depend on frequency and are set by a fundamental constant. Energy, according to this proposal, comes in packets rather than flowing smoothly. This idea of quantization was initially introduced as a mathematical fix. Planck himself was cautious about its implications. However, the results matched experimental data precisely. What had seemed like a technical adjustment turned out to reflect a deep feature of nature. Over the following decades, this principle appeared again and again. Albert Einstein applied it to explain the photoelectric effect, showing that light behaves as if it consists of discrete energy units. Niels Bohr used quantization to describe atomic structure, proposing that electrons occupy specific energy levels rather than moving freely. Experiments confirm that atoms absorb and emit energy only in specific amounts. These discoveries revealed a sharp contrast with classical motion. In classical physics, a particle can have any energy value and follow a smooth trajectory through space. In quantum mechanics, certain quantities are restricted. Energy levels are discrete. Transitions occur in jumps rather than gradual changes. This discreteness does not mean that everything is made of tiny blocks in a simple sense. Instead, it reflects limits on what can be measured and how systems behave. The mathematical structure of quantum mechanics describes probabilities rather than definite outcomes. It predicts the likelihood of finding a particle in a particular state, not a single, precise result. One of the most important consequences of this framework is uncertainty. Werner Heisenberg showed that certain pairs of physical quantities cannot both be known with arbitrary precision at the same time. Position and momentum are a key example. The more precisely a particle's position is specified, the less precisely its momentum can be determined, and vice versa. This uncertainty is not a flaw in measurement technique. It is a fundamental feature of nature as described by quantum mechanics. No improvement in instruments can remove it. The limitation arises from how physical quantities are defined and how quantum states behave. As a result, the idea of a particle following a well-defined path through space loses meaning at small scales. Between measurements, the particle does not occupy a single trajectory. Instead, it is described by a distribution of possible positions and momenta. Classical motion emerges only when these distributions are narrow enough to approximate a single path. Probability replaces certainty at a basic level. This does not mean that quantum mechanics is vague or imprecise. Its predictions are often extraordinarily accurate. What changes is the type of prediction being made. Instead of specifying exact outcomes, the theory specifies probabilities with well-defined mathematical rules. This shift has profound implications for how reality is described. In classical physics, systems have properties whether or not they are observed. In quantum mechanics, the act of measurement plays a central role. Observables such as position, energy, and spin acquire definite values only when measured. These ideas can seem abstract, but they have direct experimental support. Interference experiments with electrons and atoms show patterns that can only be explained by wave-like probability distributions. Precision measurements of atomic spectra confirm discrete energy levels with remarkable consistency. Technologies such as lasers, semiconductors, and atomic clocks rely on quantum principles and function exactly as the theory predicts. Despite its counterintuitive aspects, quantum mechanics is not optional. It is the correct description of nature at small scales. Any theory that ignores it fails to account for a vast range of observed phenomena. The contrast with classical physics is therefore stark. Classical theories describe smooth change, continuous motion, and precise trajectories. Quantum mechanics describes discrete outcomes, probabilistic behavior, and fundamental limits on measurement. The two frameworks are not merely different in detail. They rest on different assumptions about how physical quantities exist and how they can be known. This difference becomes especially important when scale is considered. At large scales, quantum effects average out. The probabilistic behavior of countless particles produces stable, predictable outcomes. This is why classical physics works so well for everyday objects. The underlying quantum structure does not disappear, but it becomes irrelevant to most practical questions. At small scales, however, the quantum description is unavoidable. Atoms, electrons, and photons do not behave classically. Their properties are quantized. Their behavior is governed by probability rather than certainty. Attempts to force classical concepts onto these systems lead to contradictions and failed predictions. This raises a critical issue when gravity and spacetime are considered. General relativity describes spacetime as smooth, continuous, and deterministic. Quantum mechanics describes matter and energy as discrete, probabilistic, and subject to uncertainty. Both theories are supported by extensive experimental evidence. Both work extremely well in their respective domains. The difficulty arises because the two frameworks make incompatible assumptions. Quantum mechanics assumes a fixed background of space and time in which particles and fields exist. General relativity treats spacetime itself as dynamic, shaped by energy and momentum. Quantum mechanics introduces uncertainty and quantization at small scales. General relativity assumes that spacetime can be subdivided without limit. When gravity is weak and scales are large, this tension can be ignored. Quantum effects are negligible, and spacetime behaves classically. When quantum effects dominate and gravity is weak, spacetime can be treated as a fixed background. Problems appear only when both gravity and quantum effects are strong at the same time. These conditions occur when matter and energy are confined to extremely small regions. They are relevant near singularities, at the beginning of cosmic expansion, and potentially at scales far beyond current experimental reach. In these regimes, neither classical spacetime nor standard quantum mechanics can be applied without modification. The appearance of quantum mechanics therefore marks a turning point. It introduces a fundamentally different description of physical reality, one that challenges the assumptions underlying smooth spacetime. It does not merely add new details to an existing framework, it changes the rules by which physical quantities are defined and related. Understanding this contrast is essential. The question of when spacetime becomes quantum is not about replacing one theory with another. It is about identifying where the assumptions of each theory cease to apply and how they might be reconciled. The quantum world does not deny the success of classical descriptions. It explains why they work where they do. At the same time, it sets clear boundaries. Beyond those boundaries, continuity, determinism, and smooth geometry can no longer be taken for granted. This is the tension that now comes into focus. A theory built on smooth spacetime meets a theory built on quantization and uncertainty. The point at which these two descriptions intersect is where the question of quantum spacetime becomes unavoidable. Once both general relativity and quantum mechanics are placed side by side, a deeper problem becomes impossible to ignore. Each theory is extraordinarily successful within its own domain, yet when their assumptions are combined, they resist fitting together into a single, coherent description. The disagreement is not about experimental detail. It runs through the foundations of how each theory understands reality. At the heart of the issue is how each framework treats space and time. In quantum mechanics, space and time are treated as a fixed background. Particles and fields exist within this background. Their properties change with time, their positions are measured within space, but the structure of space and time themselves is assumed to be stable and given. The background does not respond to what happens inside it. This assumption is known as background dependence. The geometry of spacetime is specified in advance and remains unaffected by the quantum processes unfolding within it. This approach works extremely well when gravity is negligible or when spacetime curvature is small. General relativity takes the opposite stance. It is fundamentally background independent. There is no fixed spacetime stage. Instead, spacetime itself is a dynamic entity whose geometry is determined by the distribution of mass and energy. Matter tells spacetime how to curve, and spacetime tells matter how to move. Geometry and dynamics are inseparable. This difference alone creates tension. Quantum mechanics requires a stable framework in which probabilities evolve. General relativity denies the existence of such a fixed framework. When spacetime itself is subject to change, the basic structure required by quantum theory becomes unstable. The conflict deepens when attempts are made to treat gravity using quantum methods. In quantum mechanics, forces are typically described by quantum fields. These fields fluctuate. They exchange energy in discrete amounts. Calculations involve summing over many possible interactions, each contributing to the final probability of an outcome. This approach has been spectacularly successful for the electromagnetic force and the nuclear forces. When the same techniques are applied to gravity, serious problems arise. Gravity is associated with spacetime curvature. Attempting to quantize gravity involves treating small fluctuations in spacetime geometry as quantum excitations. In principle, this sounds reasonable. In practice, the calculations produce infinities that cannot be removed or controlled. These infinities are not minor technical issues. They appear at almost every step of the calculation. Quantities that should correspond to measurable physical effects diverge to infinite values. The standard methods used to tame infinities in other quantum field theories fail in this context. This problem became clear in the mid-20th century, when physicists began exploring quantum gravity seriously. Richard Feynman, who played a central role in developing quantum electrodynamics, examined whether similar techniques could be applied to gravity. His conclusion was cautious. While it was possible to define a quantum version of gravity at low energies, the theory became unmanageable at higher energies. The mathematical structure broke down. The underlying reason is tied to how gravity couples to energy. In general relativity, all forms of energy contribute to spacetime curvature. This includes not only mass and motion, but also the energy of quantum fluctuations themselves. As calculations attempt to include smaller and smaller scales, the energy associated with these fluctuations grows. The gravitational response to that energy then feeds back into the calculation, producing ever larger contributions. The result is a runaway effect. Attempts to probe spacetime at extremely small distances require high energies. Those energies strongly distort spacetime. The more precisely the geometry is examined, the less well-defined it becomes. The mathematical expressions reflect this instability by diverging. This behavior is very different from what occurs in other quantum theories. In quantum electrodynamics, infinities appear, but can be systematically absorbed into a finite number of physical parameters through a process known as renormalization. The theory remains predictive because only a limited set of quantities need adjustment. Quantum gravity does not cooperate in the same way. New infinities appear at every level of approximation. There is no finite set of parameters that can absorb them. Predictive power is lost. This failure is not merely technical. It reflects a deeper conceptual mismatch. Quantum mechanics assumes that uncertainties apply to physical quantities defined within spacetime. General relativity treats spacetime itself as a physical quantity. Combining these ideas implies that space-time geometry should be subject to quantum uncertainty. Distances and durations would fluctuate. The notion of a sharply defined space-time geometry would lose meaning. Yet quantum mechanics relies on precise notions of time to describe how systems evolve. Probabilities change with time. States are compared at different moments. If time itself becomes uncertain, the standard formulation of quantum theory begins to unravel. This creates a circular dependency. Quantum mechanics needs a stable spacetime to function. General relativity predicts that spacetime responds dynamically to energy, including quantum energy. Each theory undermines the assumptions of the other when applied simultaneously. The disagreement also appears in how each theory treats locality. Quantum field theories assume that interactions occur at specific points in spacetime. General relativity allows spacetime itself to be curved in such a way that the notion of global simultaneity disappears. There is no universal time slicing the universe into moments. This complicates the definition of quantum states that evolve uniformly. Despite these issues, it is important to be clear about what is not happening. There is no experimental contradiction between quantum mechanics and general relativity in regimes where both have been tested. The problem arises only when both quantum effects and strong gravity are present at the same time. In most laboratory experiments, gravity is so weak that it can be ignored. In most astronomical contexts, quantum effects average out. This separation of scales allows both theories to coexist without conflict in practice. The difficulty appears when scale is pushed to extremes, near black hole singularities, at the earliest moments of cosmic expansion, or when attempting to describe spacetime at distances far smaller than anything currently accessible to experiment. In these regimes, neither theory can be safely applied without modification. General relativity predicts conditions where spacetime curvature becomes infinite. Quantum mechanics predicts fluctuations that cannot be ignored. Each theory signals that its assumptions are being violated. This is why the question of quantum spacetime remains unresolved. It is not due to lack of effort or imagination. It arises because the foundational principles of the two most successful theories in physics pull in different directions. One framework treats spacetime as a smooth, deterministic geometry. The other treats physical quantities as probabilistic and quantized. When spacetime itself is included among those quantities, the mathematical and conceptual structure becomes unstable. This instability points toward an important conclusion. The problem is not that one theory is correct and the other is wrong. Both are correct within their domains. The problem is that neither is complete. Resolving this disagreement likely requires a new framework that reduces to general relativity at large scales and to quantum mechanics at small scales. Such a framework would need to explain how smooth spacetime emerges from a deeper description, and why quantum effects become negligible in ordinary conditions. Until such a framework is found, the conflict remains a guide rather than a failure. It marks the boundary between what is well understood and what is not. The disagreement between quantum mechanics and gravity is therefore not a flaw in physics. It is a signal. It points to scale as the deciding factor and suggests that the nature of spacetime depends on how closely it is examined. When disagreements appear between successful physical theories, The cause is often not location, material or environment, but scale. The same object can behave in entirely different ways depending on how closely it is examined. Physics does not offer a single description that applies unchanged at all distances and energies. Instead, it provides layers of description, each suited to a particular range of scale. This idea is familiar even outside physics. A coastline looks smooth when seen from high altitude. From closer up, it becomes jagged. At the scale of individual rocks and grains of sand, the idea of a smooth line stops being useful altogether. The object has not changed, only the scale of observation has. Physical laws behave in much the same way. At human scales, objects obey classical mechanics. Motion appears continuous. Forces produce smooth acceleration. Space and time behave as stable backgrounds. These assumptions work because the relevant scales are large compared to the microscopic structure of matter and energy. At atomic scales, the picture changes. Electrons do not orbit nuclei like small planets. Energy levels become discrete. Probabilities replace trajectories. Quantum mechanics becomes essential, not because classical physics is wrong, but because it averages over details that now matter. At even larger scales, such as those of stars, galaxies, and the universe as a whole, gravity dominates. General relativity provides the appropriate description. Spacetime curvature governs motion. Time flows at different rates depending on gravitational conditions. Quantum effects remain present, but they're usually negligible because they average out across vast numbers of particles. Each of these descriptions is accurate within its range. Problems arise only when a description is pushed beyond the scale where its assumptions hold. This perspective reframes the question of quantum spacetime. The issue is not where spacetime becomes quantum in the sense of a particular place or region. It is when, meaning at what scale, the smooth geometric description ceases to be sufficient. To make this concrete, consider the range of scales involved. An atom is roughly 1/10 billionth of a meter across. A human being spans about 1 meter. Earth's diameter is roughly 12 million meters. The observable universe stretches for tens of billions of light years, each light year being nearly 10 trillion kilometers. These scales differ by many orders of magnitude. It would be surprising if the same description applied unchanged across this entire range. Physics has long recognized this and built methods to manage it. One such method is the idea of effective theories. An effective theory describes phenomena at a particular scale without attempting to capture all underlying details. It works because those details do not significantly influence the behavior being studied. Classical mechanics is an effective theory. It ignores atomic structure and quantum uncertainty, yet accurately predicts the motion of cars, planets, and spacecraft. Fluid dynamics is another effective theory. It treats liquids as continuous substances even though they're made of discrete molecules. The theory succeeds because molecular details average out at larger scales. Smooth spacetime may be an effective description in the same sense. At scales accessible to observation and experiment, spacetime behaves as a continuous geometric structure. Curvature changes gradually. Distances and durations can be measured precisely. The mathematics of general relativity works because it captures the dominant behavior at those scales. If spacetime has a more fundamental structure at extremely small distances, that structure may be irrelevant to most physical processes. Just as the graininess of matter does not affect planetary motion, the graininess of spacetime would not affect everyday experience. This idea is closely connected to renormalization, a set of techniques developed in quantum field theory to deal with how physical behavior changes with scale. Renormalization formalizes the notion that different descriptions apply at different resolutions. As one moves from small scales to large ones, certain details fade away, while others become dominant. In this framework, parameters such as mass, charge, and coupling strength depend on the scale at which they are measured. The laws themselves do not change, but their effective expression does. What matters at one scale may be negligible at another. Applied to spacetime, this suggests a possibility. The smooth geometry described by general relativity may emerge from a more complex underlying description when viewed at large scales. At smaller scales, new degrees of freedom may become relevant, altering how spacetime behaves. Emergence is not a speculative concept. It is a well-established feature of many physical systems. Temperature emerges from molecular motion. Pressure emerges from particle collisions. Elasticity emerges from atomic bonds. None of these properties exist at the level of individual particles, yet they are real and measurable at larger scales. Spacetime smoothness could be similar. It may not be fundamental. It may be a large-scale property that arises when microscopic details are averaged over. This perspective helps clarify why general relativity works so well. It is not because spacetime is fundamentally smooth at all scales, but because the smooth description captures the relevant physics where measurements are made. The theory is accurate because it is applied where it is valid. It also explains why problems appear only under extreme conditions. Singularities arise when matter and energy are compressed into very small volumes. Quantum fluctuations become significant when distances shrink. These are precisely the regimes where scale matters most and where effective descriptions are most likely to fail. Seen this way, the disagreement between quantum mechanics and general relativity is not mysterious. Each theory is an effective description tailored to a different scale. Quantum mechanics governs small systems with strong fluctuations. General relativity governs large systems where geometry dominates. The difficulty arises in the narrow overlap where both effects are important. This overlap is small but crucial. It includes conditions near black hole singularities, the earliest moments of cosmic expansion, and any attempt to probe spacetime at extremely short distances. In these regimes, neither classical geometry nor standard quantum theory can be applied without qualification. Framing the problem in terms of scale also helps avoid a common misconception. The question is not whether spacetime is quantum here or classical there. It is not about particular locations in the universe. It is about resolution. The same region of space can appear smooth at one scale and non-smooth at another. A table looks solid from a distance. Under a microscope it reveals structure. At the level of atoms it is mostly empty space. The object has not changed. The description has. The same may be true of spacetime. If spacetime becomes quantum only at scales far smaller than anything currently accessible, then its quantum nature would not contradict everyday experience or astronomical observation. It would simply lie beyond the resolution of existing measurements. This does not diminish the importance of the question, it sharpens it. Instead of asking where spacetime changes, the focus shifts to how small one must look before the smooth description breaks down. Understanding scale as the key variable allows the problem to be posed precisely. It also prepares the ground for the introduction of fundamental limits. If there is a smallest meaningful length or time, that limit would define the scale at which spacetime's effective smoothness ends. The search for that scale is not about finding a hidden boundary in space. It is about identifying the point at which our current descriptions must give way to something deeper. As attention moves towards smaller and smaller scales, one particular length keeps appearing in theoretical physics. It is not derived from measurement or experiment, but from the basic constants that govern nature. This length is known as the Planck length, and it plays a central role in discussions about quantum spacetime. The Planck length is named after Max Planck, who introduced the idea of fundamental natural units at the beginning of the 20th century. Planck was interested in identifying quantities that do not depend on human conventions such as meters or seconds, but instead arise directly from the structure of physical law. To construct such units, Planck combined constants that appear in both quantum mechanics and gravity. One constant sets the scale of quantum effects, another governs the strength of gravity. A third links space and time through the speed of light. When these constants are combined in a specific way, the result is a length scale. That length is extraordinarily small. The Planck length is approximately 1.616 times 10 to the power of minus 35 meters. Compared to everyday distances, it is unimaginably tiny. For context, an atom is about 1/10 billionth of a meter across. A proton is roughly 1,000 times smaller than an atom. The Planck length is far smaller still. There are as many Planck lengths in a proton as there are protons in the observable universe. Despite its extreme smallness, the Planck length is not arbitrary. It marks the scale at which quantum mechanics and gravity become equally important. At larger distances, gravity dominates large-scale structure, while quantum effects average out. At atomic scales, quantum mechanics governs behavior, while gravity becomes negligible. The Planck length sits at the intersection of these two regimes. It is the scale at which attempts to localize energy strongly enough to probe smaller distances would inevitably produce strong gravitational effects. This is not a matter of technological limitation. It is a consequence of physical law. To measure a very small distance, a probe with very short wavelength is required. Shorter wavelength means higher energy. As the energy of the probe increases, its gravitational influence increases as well. At sufficiently high energy, concentrating that energy into a small region would cause spacetime itself to respond strongly. Beyond a certain point, increasing energy does not improve resolution. Instead, it distorts the region being measured. If enough energy is confined within a sufficiently small volume, the result would be the formation of a black hole. At that point, information about smaller distances becomes inaccessible. The Planck length emerges as the scale where this transition occurs. Below this scale, the very act of measurement disrupts spacetime so severely that the concept of distance loses operational meaning. It is no longer clear what it would mean to say that two points are separated by a smaller length. This is why the Planck length is often described as a minimum measurable length, though that phrase requires care. It does not necessarily mean that spacetime is made of discrete chunks of that size. Rather, it indicates that the usual procedures for defining and measuring distance cease to function. Operational meaning matters in physics. A quantity is considered physically meaningful only if there is, at least in principle, a way to measure it. If no possible experiment can distinguish one value from another, then the distinction may not correspond to anything real. At distances smaller than the Planck length, no known measurement process can resolve structure without invoking energies that destroy the very notion of spacetime geometry. This suggests that talking about smaller distances may be physically meaningless, even if mathematical descriptions can still be written down. This idea represents a shift in perspective. Classical geometry assumes that distance can always be subdivided further. Quantum mechanics challenges this assumption by introducing uncertainty. Gravity reinforces the challenge by making spacetime itself dynamic and sensitive to energy. Together, these effects imply a fundamental limit. It is important to be precise about what this limit does and does not say. The Planck length is not a boundary that has been observed. No experiment has directly probed distances anywhere near this scale. It is a theoretical construct derived from combining well-established constants. Its significance lies in what it tells us about consistency. If both quantum mechanics and general relativity are correct within their domains, then there must be a scale at which neither can be applied independently. The Planck length identifies that scale. This is why it appears repeatedly in discussions of quantum gravity. It sets the point at which the smooth description of spacetime provided by general relativity is expected to fail, not gradually, but structurally. Above the Planck length, spacetime behaves in a way that can be approximated as continuous. Below it, the assumptions underlying continuity may no longer hold. The theory does not say what replaces smooth geometry. It says only that smooth geometry cannot be assumed indefinitely. Some theoretical approaches suggest that spacetime may become discrete at this scale, with areas and volumes taking on quantized values. Others suggest that spacetime may be fundamentally relational, with geometry emerging from more basic interactions. Still others propose that spacetime itself is not fundamental at all. What these approaches share is the recognition that the Planck length marks a limit to the classical notion of distance. Another way to understand this is to consider dimensional analysis. The constants used to define the Planck length are not chosen arbitrarily. One governs quantum uncertainty, one governs gravitational strength, one governs the conversion between space and time. Any attempt to describe spacetime at the smallest scales must involve all three. This makes the Planck length a natural scale rather than a human-chosen one. It is not introduced to fix a problem in a calculation. It emerges from the structure of the theories themselves. This also explains why smaller lengths do not naturally appear in established physics. There is no known mechanism that allows spacetime structures to be probed meaningfully below this scale. Any attempt to do so runs into the same fundamental obstacle: energy concentration leading to gravitational collapse. The Planck length therefore acts as a conceptual boundary. It does not tell us what spacetime is made of. It tells us where our current descriptions stop making sense. This boundary should not be confused with certainty. Physics has encountered apparent limits before that were later reinterpreted. What makes the Planck length different is that it arises from combining theories that have already been tested extensively. It is not an artifact of incomplete data, but of theoretical consistency. That said, caution is essential. The Planck length is a guide, not a measurement. It points to where new physics is required, but it does not specify what that physics must look like. Treating it as a literal smallest unit of space risks overstating what is known. What can be said with confidence is this: if spacetime becomes quantum in any meaningful sense, it is expected to occur at or near the Planck length. That is where quantum uncertainty, gravitational interaction, and spacetime structure converge. Above this scale, smooth geometry works extremely well. Below it, distance itself becomes an unstable concept. The language of points, lengths, and intervals begins to lose physical grounding. This makes the Planck length a turning point in the discussion. It provides a scale at which questions about quantum spacetime become unavoidable rather than speculative. The next step is to understand why measurement fails so completely at this scale, and what that failure implies about the nature of spacetime itself. Time is usually treated as the most reliable ingredient in physical description. Events occur, time passes, and the order of cause and effect feels fixed. Even when space is curved or distorted, time still appears to provide a steady sequence in which physics unfolds. Classical mechanics depends on this assumption, and even general relativity, for all its flexibility, preserved a continuous notion of duration. If distance can reach a limit where the idea of length loses operational meaning, it is reasonable to ask whether time faces a similar constraint. The temporal analogue of the Planck length is known as the Planck time. It is defined as the time light would take to travel one Planck length in a vacuum. Like the Planck length, it is constructed by combining the constants that govern quantum mechanics, gravity, and relativity. It does not arise from experiment, but from consistency between theories that are already well tested. Numerically, the Planck time is on the order of 10 to the minus 43 seconds. This is not merely small by human standards. It is vastly smaller than any time interval that could be measured, produced, or resolved by any known physical process. Its significance lies not in its value, but in what it represents. In everyday physics, time intervals can be made shorter by using faster clocks or more energetic processes. Atomic clocks measure time using oscillations within atoms, reaching extraordinary precision. Particle physics experiments probe interactions occurring over extremely brief intervals. In all of these cases, time behaves as a continuous parameter that can be subdivided further as technology improves. Quantum mechanics complicates this picture by linking time and energy. Processes that occur over very short durations involve large uncertainties in energy. This is not a limitation of instruments. It is a fundamental feature of how quantum systems behave. Shorter times require higher energies to resolve meaningfully. On its own, this does not imply a minimum time. Quantum mechanics allows arbitrarily short intervals in principle. The difficulty appears when gravity is included. High energy densities distort spacetime. This is not a secondary effect. It is the central insight of general relativity. Energy and momentum determine how spacetime curves. If an attempt is made to probe a time interval comparable to the Planck time, the energy required becomes so large that it strongly affects the geometry of spacetime itself. At that point, the concept of a sharply defined time interval begins to fail. Just as with distance, measurement undermines itself. The physical process used to define the interval alters the spacetime structure in which the interval is being defined. The notion of a clean separation between one moment and the next becomes unstable. This instability has consequences for causality. Causality depends on the ordering of events. One event causes another if it precedes it in time, and can influence it through physical processes. General relativity refines this idea by tying causal structure to spacetime geometry. Light cones define which events can influence which others. Even in curved spacetime, causal order remains well defined. At extremely small timescales, this structure becomes uncertain. If spacetime itself fluctuates due to quantum effects, then the light cones that define causal relationships also fluctuate. The clear distinction between before and after can blur. This does not mean that causality disappears in any everyday sense. It means that the classical notion of sharply ordered time intervals may not apply at the smallest scales. Cause and effect may still exist, but not in a form that maps cleanly onto classical time. This issue becomes especially important when considering the early universe. Cosmological models based on general relativity describe an expanding universe that was denser and hotter in the past. As this expansion is traced backward, time intervals shrink and energy densities rise. Eventually, the equations predict a state of extreme density at the beginning of expansion. Near this beginning, often associated with the earliest moments of cosmic history, the timescales involved approach the Planck time. In this regime, classical spacetime cannot be assumed to exist in its usual form. Quantum fluctuations in geometry would have been unavoidable. This does not mean that the universe began at a specific instant in the classical sense. It means that the concept of time itself may not extend meaningfully beyond a certain point. Asking what happened before that point may be like asking what lies north of the North Pole. The question assumes a structure that may no longer apply. Importantly, the Planck time should not be interpreted as the smallest tick of a universal clock. There is no evidence that time advances in discrete steps of this duration. Many theories of quantum gravity do not predict time quantization in that simple sense. Instead, the Planck time marks a boundary for classical description. It identifies the scale at which treating time as a smooth, continuous parameter ceases to be justified without modification. Above this scale, time behaves in ways that align with both experience and experiment. Clocks can be synchronized, durations can be compared, cause and effect are ordered. Below it, the assumptions underlying these concepts are no longer secure. This mirrors what was seen with distance. The Planck length does not prove that space is made of indivisible units. It indicates that the concept of distance loses operational meaning below a certain scale. The same applies to duration. Time, like space, may be emergent. It may arise from more fundamental processes that only approximate continuity when viewed at large scales. At very small scales, the language of moments and intervals may not correspond to anything physically real. This perspective helps reconcile why time works so well in classical and relativistic physics. It is not because time is fundamental in all regimes, but because it is an effective concept that applies where fluctuations are negligible and geometry is stable. Recognizing a limit to classical duration does not undermine physics. It clarifies its scope. It explains why attempts to describe the earliest universe or the interior of black holes encounter conceptual breakdowns rather than smooth extrapolations. The Planck time therefore serves as a marker. It signals where familiar notions of time reach the edge of their usefulness. Beyond that edge, new descriptions are required, not because time vanishes, but because the classical idea of duration no longer applies. Together with the Planck length, it reinforces a consistent picture. Smooth spacetime with continuous distances and durations is an excellent description at accessible scales. At sufficiently small scales, both space and time may require a different foundation. The breakdown of continuity is not an anomaly, it is a clue. It points toward a deeper structure in which space-time, as it is usually understood, emerges only when viewed from far enough away. At sufficiently small scales, the idea of an empty, featureless vacuum no longer holds. What appears as nothingness in classical physics becomes active in quantum theory. Even in the absence of particles, space is not truly empty. It is filled with fluctuations that arise from the basic structure of quantum mechanics. These are known as vacuum fluctuations. In quantum mechanics, fields exist everywhere, even where no particles are present. Each field possesses a minimum amount of energy, called zero-point energy. This energy cannot be removed. It is not associated with motion, heat, or radiation in the usual sense. It is a consequence of the uncertainty inherent in quantum systems. A useful way to understand this is to consider that quantum fields cannot be perfectly still. Just as a particle cannot have both a perfectly defined position and momentum, a field cannot have both exactly zero energy and a perfectly fixed configuration. As a result, even the lowest possible energy state involves fluctuations. These fluctuations are not merely mathematical artifacts, they have observable consequences. One example is the Casimir effect, where two uncharged metal plates placed very close together experience a measurable force due to changes in the quantum vacuum between them. Another is the spontaneous emission of light by excited atoms, which occurs because the vacuum itself is not static. In most contexts, these effects are extremely small. They average out and have little influence on large-scale behavior. But when gravity is considered, the situation changes. General relativity teaches that energy influences spacetime geometry. Any form of energy, including zero-point energy, contributes to curvature. If quantum fields fluctuate, then the energy associated with those fluctuations should also fluctuate. If energy fluctuates, spacetime geometry should respond. This leads to a striking possibility. At very small scales, spacetime itself may fluctuate. Instead of being a smooth geometric structure, spacetime may exhibit constant rapid variations in curvature. Distances and angles would not be fixed. They would shift and blur due to underlying quantum effects. The classical picture of a stable background would no longer apply. This idea was explored in detail by John Wheeler, a physicist who made major contributions to both general relativity and quantum theory. Wheeler recognized that if quantum mechanics applies to everything else in nature, it should also apply to spacetime itself. He proposed that at extremely small scales, spacetime might be wildly irregular. He described this hypothetical regime as quantum foam. The term is metaphorical, but it conveys an important point. Just as foam consists of bubbles forming, merging, and collapsing, quantum spacetime might involve constant creation and annihilation of geometric features. Tiny distortions, tunnels, or fluctuations could appear and disappear on extremely short timescales. It is important to be clear about what this picture does and does not claim. Quantum foam is not a confirmed description of reality. It is a conceptual image meant to capture the idea that spacetime may not be smooth when examined closely enough. The details depend on the correct theory of quantum gravity, which has not yet been established. Nevertheless, the concept serves an important role. It provides a way to visualize how smooth spacetime might break down without invoking literal discreteness or sharp boundaries. In this view, spacetime is not made of rigid blocks. Instead, it is more like a restless medium whose average behavior appears smooth, while its microscopic behavior is highly irregular. The scale at which this behavior becomes relevant is expected to be near the Planck length and Planck time. At these scales, quantum fluctuations of energy are strong enough to produce significant fluctuations in curvature. The geometry of spacetime would no longer be well defined in the classical sense. This does not mean that spacetime dissolves into chaos in any observable way. These fluctuations would be confined to scales far smaller than anything directly accessible. At larger scales, the fluctuations would average out, producing the smooth geometry described by general relativity. This averaging process is central to why classical spacetime works so well. Just as thermal motion of atoms produces smooth temperature at macroscopic scales, quantum fluctuations of spacetime could produce smooth geometry when viewed from far enough away. The idea of quantum foam also highlights why measurement becomes so difficult at these scales. If spacetime itself is fluctuating, then the concept of a fixed ruler or clock becomes problematic. any measuring device would be embedded in the same fluctuating geometry it is attempting to measure. This undermines the assumption that distances and durations can be defined independently of the measurement process. Instead, geometry becomes relational and context-dependent. What can be said depends on how the system is probed. Wheeler emphasized that this regime is not one where familiar intuition should be trusted. Concepts such as points, trajectories, and continuous paths may no longer apply. The mathematics used to describe smooth manifolds may fail because the underlying structure does not support them. At the same time, it is crucial to avoid overstating the implications. Quantum foam does not imply that spacetime is literally boiling or unstable in any macroscopic sense. It does not mean that spacetime is tearing itself apart. The effects are confined to scales where classical language breaks down. From a physical standpoint, quantum foam represents a region where known theories overlap but do not fully agree. Quantum mechanics predicts fluctuations. General relativity predicts that energy affects geometry. Combining these predictions suggests fluctuating geometry, but does not provide a complete description. Different approaches to quantum gravity treat this situation differently. Some predict discrete geometric structures, others predict smooth but highly fluctuating geometries. Some suggest that spacetime itself emerges from more fundamental entities that are not geometric at all. What unites these approaches is the rejection of smooth spacetime as a fundamental assumption at all scales. Instead, smoothness becomes something that emerges when fluctuations are averaged over large distances and long times. The imagery of quantum foam helps bridge the gap between abstract theory and physical intuition. It allows one to think about spacetime not as a static stage, but as an active participant subject to quantum effects. This shift in perspective is significant. Once spacetime is allowed to fluctuate, it becomes clear why attempts to quantize gravity face such difficulties. The object being quantized is not a field within spacetime, but spacetime itself. It also clarifies why classical geometry reappears so reliably. The foam does not disappear. It becomes irrelevant at scales where fluctuations cancel out and geometry stabilizes. In that sense, quantum foam is not a competing description of spacetime. It is a candidate for what lies beneath it. Whether this picture is correct remains an open question. What matters here is the role it plays in thinking about quantum spacetime. It provides a concrete way to imagine how continuity might fail without abandoning physical realism. Spacetime in this view is neither perfectly smooth nor fundamentally broken. It is structured in a way that depends on scale. At large scales, it behaves like a continuous geometric entity. At the smallest scales, it may be dominated by quantum fluctuations that defy classical description. This non-smooth microscopic picture marks a transition in the discussion. The focus shifts from whether spacetime can be treated as smooth to what replaces smoothness when it cannot. The language necessarily becomes more tentative here, not because physics becomes speculative, but because current theories reach their limits. What can be said with confidence is limited but not trivial. Quantum fluctuations of spacetime offer a coherent reason why smooth geometry should fail at small scales while remaining accurate at large ones. They connect quantum uncertainty, gravitational response, and the emergence of classical spacetime into a single conceptual framework. This does not provide a final answer. It provides a direction. It suggests that spacetime's quantum nature, if it exists, is not static or discrete in a simple sense, but dynamic, relational, and scale-dependent. The imagery of foam may not survive future theories. The underlying insight likely will. The phrase quantum foam is often the first image people encounter when thinking about space-time at the smallest scales. It suggests motion, instability, and structure, where classical physics expects smoothness. As an idea, it is useful. As a literal description, it can be misleading. Understanding what the term is meant to convey and what it is not is essential. At its core, quantum foam is an attempt to describe what spacetime might be like when quantum effects become unavoidable. It arises from combining two well-established facts. Quantum mechanics predicts unavoidable fluctuations in energy. General relativity predicts that energy affects spacetime geometry. If both statements are taken seriously, then spacetime geometry itself should fluctuate at sufficiently small scales. That conclusion is conceptually straightforward. Visualizing it is not. The human mind tends to picture space as an empty container and time as a flowing sequence. Foam suggests bubbles forming and popping within that container. This is not what is meant. There is no background space in which space-time foam sits. The fluctuations are not happening in space-time. They are fluctuations of space-time. This distinction matters. When John Wheeler introduced the term, he was not proposing a specific physical structure. He was pointing to a regime where classical geometric language breaks down. The foam was meant to signal the loss of smoothness and predictability, not to specify the exact form of what replaces it. At extremely small scales, the quantities that define geometry in general relativity, such as distance, angle, and curvature, may not have stable values. Instead of a single well-defined geometry, there may be a range of possible geometries, each contributing probabilistically. In that sense, spacetime would behave more like a quantum system than a classical object. The word foam captures this multiplicity. It suggests a constantly changing pattern rather than a fixed structure. But it is a metaphor, not a model. Metaphors are useful because they allow unfamiliar ideas to be discussed using familiar language. They are dangerous when taken too literally. Quantum foam does not imply bubbles of space, popping in and out of existence in any simple or observable way. It does not imply turbulence or motion that could be detected by instruments. It does not imply instability at scales larger than the Planck regime. The foam, if it exists, would be confined to scales far smaller than anything that could influence ordinary physics. One way to keep this grounded is to remember that the foam is not a claim about appearance. It is a claim about calculation. When physicists attempt to describe spacetime using quantum principles, the mathematics suggests that contributions from many possible geometries must be considered. The smooth geometry of general relativity appears only as an average over these possibilities. In this sense, the foam is statistical rather than mechanical. It is not a substance. It is a way of talking about uncertainty and fluctuation in geometry. This also explains why visualization is limited. Human intuition is built around objects moving through space over time. Quantum foam challenges both ideas at once. There may be no fixed objects, no stable background, and no single timeline. Any picture that resembles familiar physical scenes is likely to mislead. This is why careful language is important. Saying that spacetime is foamy does not mean it is chaotic in the everyday sense. It means that classical descriptions fail to capture its behavior at certain scales. It also means that different theories can use the same metaphor while meaning different things. In some approaches to quantum gravity, spacetime is fundamentally discrete. In others, it is continuous but subject to large quantum fluctuations. In still others, spacetime emerges from more basic entities that are not geometric at all. All of these approaches might be loosely described as involving quantum foam, but they are not equivalent. The metaphor unifies them only at a very high level. This is where speculation enters the picture. Quantum foam has not been observed. There's no experimental evidence that directly confirms or rules out its existence. Its status is theoretical, inferred from the attempt to reconcile quantum mechanics with gravity. That makes it a plausible idea, not an established fact. Acknowledging this is not a weakness, it is a strength. Physics progresses by clearly distinguishing what is known, what is inferred, and what is unknown. What is known is that quantum fields fluctuate. What is known is that energy affects spacetime geometry. What follows from combining these facts depends on assumptions about how quantum principles apply to spacetime itself. That is where different theories diverge. The foam metaphor helps prevent a different kind of misunderstanding as well. It discourages the idea that spacetime must either be perfectly smooth or completely broken into rigid pieces. The reality may be more subtle. Spacetime may lack a fixed structure at small scales without being composed of simple building blocks. This middle ground is difficult to describe without imagery, which is why metaphors persist despite their limitations. Another important point is that quantum foam does not imply randomness without structure. Quantum mechanics is probabilistic, but it is not arbitrary. Probabilities follow precise mathematical rules. If spacetime fluctuates quantum mechanically, those fluctuations would also follow well-defined laws, even if the outcomes are not deterministic. From this perspective, foam does not mean disorder. It means indeterminacy constrained by physical principles. The usefulness of the concept lies in how it reframes expectations. Instead of assuming that spacetime must remain smooth at all scales, it allows for the possibility that smoothness is an emergent property. Instead of expecting a single geometry, it allows for many possible geometries contributing collectively. This prepares the ground for more formal approaches. Once the metaphor has done its job, it must be set aside. Progress depends on precise mathematical frameworks, not imagery. The foam is a bridge, not a destination. It also serves as a caution. Overly concrete images can create false confidence. Thinking of spacetime as frothy or bubbling can make the unknown feel familiar when it is not. The goal here is not comfort, but clarity. In summary, quantum foam is best understood as a conceptual signal. It marks the breakdown of smooth spacetime at very small scales. It captures the idea that geometry itself may be subject to quantum uncertainty. It does not specify the detailed structure of spacetime, nor does it claim direct observability. Treating it as a metaphor keeps it useful. Treating it as a literal picture leads to confusion. With that distinction in place, attention can shift toward theories that attempt to describe quantum spacetime without relying on imagery. The foam has served its purpose by loosening classical assumptions. What comes next requires more precise tools. One serious attempt to reconcile quantum mechanics with gravity begins by taking general relativity at face value. Instead of treating gravity as a force added to quantum theory, this approach starts with spacetime itself and asks how its geometry might behave if quantum principles are applied directly to it. This line of thought is known as loop quantum gravity. The central idea behind loop quantum gravity is straightforward in spirit, even if technically demanding. If spacetime is dynamic, as general relativity insists, and if quantum mechanics applies universally, then spacetime geometry itself should be subject to quantization. Distances, areas, and volumes should not vary continuously without limit, but should come in discrete amounts. This approach does not attempt to unify all forces of nature, It does not introduce extra dimensions or new particles beyond those already known. Its goal is narrower but deeper. It aims to describe the quantum properties of spacetime itself. Two physicists closely associated with the development of this framework are Carlo Rovelli and Lee Smolin. Working independently and collaboratively from the late 20th century onward, they helped shape the mathematical structure of loop quantum gravity and clarify its physical interpretation. One of the key conceptual moves in loop quantum gravity is the abandonment of a fixed background spacetime. This choice aligns the theory closely with general relativity. There is no predefined geometry on which quantum processes unfold. Instead, geometry is part of the quantum system. This makes loop quantum gravity a background-independent theory. Spacetime does not exist first, with quantum effects layered on top. Geometry emerges from the quantum states themselves. To describe these states, the theory introduces a new way of representing geometry. Instead of smooth fields defined at every point, geometry is encoded in networks of discrete elements known as spin networks. A spin network is not a physical object embedded in space. It is a mathematical structure that represents how areas and volumes are related. The nodes of the network correspond to elementary chunks of volume. The links between nodes correspond to elementary areas. Together they define a quantum state of geometry. Each link carries a quantum number that determines the amount of area it represents. Each node carries information about volume. These quantities are not continuous. They take on discrete values, much like the energy levels of an atom. This leads to one of the most striking predictions of loop quantum gravity. Geometric quantities such as area and volume have minimum non-zero values. There is a smallest possible area and a smallest possible volume. Space in this sense is not infinitely divisible. It is important to state this carefully. Discreteness here does not mean that space is made of tiny cubes arranged on a grid. The geometry is relational rather than lattice-like. The spin network does not sit inside space. It defines space. At large scales, when many such elements are involved, the discrete structure becomes indistinguishable from a smooth continuum. The familiar geometry of general relativity emerges as an approximation, just as fluid flow emerges from molecular motion. This emergence is central to the credibility of the theory. Any viable approach to quantum gravity must reproduce classical spacetime at scales where general relativity has been tested. Loop quantum gravity is constructed so that this limit exists in principle, though demonstrating it in full detail remains an active area of research. Time is treated differently as well. In loop quantum gravity, there is no single universal time parameter. Instead, change is described relationally. Physical quantities evolve with respect to one another rather than with respect to an external clock. This reflects a lesson already present in general relativity. Time is not an absolute background variable. It is tied to the geometry and matter content of the universe. Loop quantum gravity extends this idea into the quantum domain. One consequence of this is that the theory does not predict spacetime foam in the pictorial sense often imagined. Instead of wildly fluctuating geometry at every scale, the theory predicts a granular but well-defined structure. The uncertainty lies in which spin network configuration describes a given situation, not in the stability of the geometry once a configuration is specified. This distinction matters. Loop quantum gravity does not suggest that spacetime becomes chaotic at small scales. It suggests that spacetime has a definite quantum structure, governed by precise mathematical rules. These rules lead to specific predictions. One of the most studied concerns the fate of classical singularities. In certain simplified models, loop quantum gravity replaces singularities with finite, well-behaved quantum states. Instead of infinite density, the theory predicts a transition through a minimum volume. Applied to cosmology, this idea leads to scenarios in which the classical beginning of expansion is replaced by a quantum bounce. The universe contracts to a very small but finite size, then expands again. Time does not end. The classical description simply ceases to apply. It is important to be clear about the status of these results. They are derived within simplified settings that capture key features of the full theory, but do not represent complete solutions. They demonstrate consistency rather than certainty. Another area of interest is black hole physics. Loop quantum gravity predicts that the area of a black hole horizon is quantized. This provides a microscopic explanation for black hole entropy, connecting geometric degrees of freedom to thermodynamic behavior. Here again, the results are suggestive rather than final. They show that the theory can reproduce known semi-classical results, while offering new insight into their origin. Despite these successes, loop quantum gravity faces significant challenges. The mathematics is complex. Connecting the discrete quantum geometry to smooth spacetime in all situations is technically demanding. Making contact with experiment is difficult because the predicted effects occur at scales far beyond current reach. There is also the question of completeness. Loop quantum gravity focuses on spacetime geometry and gravity. It does not automatically incorporate the other fundamental forces or the particles described by the standard model. Whether and how these elements can be included remains an open problem. These limitations are acknowledged by researchers working in the field. They are not viewed as failures, but as indicators of how difficult the problem truly is. What gives loop quantum gravity its standing as a serious candidate theory is not that it provides all the answers, but that it is built on clear principles. It respects the background independence of general relativity. It applies quantization to geometry itself. It produces concrete, testable mathematical predictions, even if those predictions are currently inaccessible. Equally important is what the theory does not assume. It does not rely on extra dimensions. It does not require unobserved symmetries. It does not posit a pre-existing spacetime arena. Everything begins with the geometry we already know and asks how it behaves under quantum rules. This makes loop quantum gravity conceptually conservative, even as it is mathematically radical. Its picture of spacetime is neither perfectly smooth nor wildly fluctuating. It is discrete, relational, and structured. Smoothness emerges only when many quantum geometric elements are considered together. This offers one clear answer to the question of when spacetime becomes quantum. In this approach, spacetime is always quantum. What changes with scale is whether that quantum nature is visible or hidden by averaging. At large scales, quantum geometry looks classical. At small scales, discreteness becomes unavoidable. Loop quantum gravity does not claim to be the final word. It claims to be a consistent step. It shows that it is possible to construct a theory in which spacetime itself is quantized without abandoning the core insights of general relativity. Whether this approach is correct remains unknown. What it provides is a concrete example of how the smooth spacetime of experience might arise from a deeper quantum structure, and how continuity could fail without destroying coherence. In doing so, it sets a standard against which other approaches can be compared. Another major attempt to understand quantum spacetime begins from a very different starting point. Rather than quantizing spacetime geometry directly, this approach asks whether the basic ingredients of matter and force have been correctly identified in the first place. This line of thought leads to what is known as string theory. The core premise of string theory is simple to state. The fundamental constituents of nature are not point-like particles, but extremely small extended objects called strings. These strings can vibrate in different ways. Each pattern of vibration corresponds to a different particle, with its own mass and properties. In this picture, particles such as electrons, quarks, and even force carriers are not fundamentally distinct. They are different modes of the same underlying object. What appears as diversity at low energies is unity at the smallest scales. This idea emerged in the late 20th century as physicists searched for a consistent way to describe gravity using quantum principles. Early attempts to quantize gravity directly ran into the problem of uncontrollable infinities. String theory offered a way around this by softening interactions at very small distances. Point particles interact at single locations, leading to sharp divergences in calculations. Strings, by contrast, have spatial extent. Interactions are spread out along the string, which smooths out the behavior at short distances. This mathematical feature turns out to be crucial. One of the most important results of string theory is that gravity is not added by hand. It appears naturally. Certain vibrational modes of strings behave exactly like a quantum particle that carries gravitational interaction. In other words, a quantum description of gravity emerges automatically from the theory. This was a major motivation for pursuing the framework further. A single theoretical structure seemed capable of incorporating both quantum mechanics and gravity, something no other approach had achieved so cleanly. The ambition of string theory goes beyond gravity alone. Its broader goal is unification. It aims to describe all fundamental forces and particles within a single, consistent framework. Electromagnetism, the nuclear forces, and gravity would all arise from the same underlying dynamics. This unifying ambition has shaped much of theoretical physics over the past several decades. Large communities of researchers have explored the mathematical structure of string theory, often working in close dialogue with developments in particle physics, cosmology, and mathematics. The research culture surrounding high-energy physics reflects this. Ideas developed in string theory circulate through conferences, institutes, and collaborations associated with major experimental centers, including those focused on particle collisions and fundamental interactions. Even when string theory itself cannot be tested directly, its influence shapes how questions are framed and which problems are considered meaningful. One of the most striking features of string theory is that it requires more dimensions of space than are directly observed. In its simplest consistent forms, string theory requires a total of 10 spacetime dimensions. That means 9 dimensions of space and 1 of time. Other versions require even more. This immediately raises an obvious question. If extra dimensions exist, why are they not seen? The standard answer is that these additional dimensions are compactified. They are curled up into extremely small shapes, far smaller than any scale that could be detected with current technology. At human and even atomic scales, these dimensions would be invisible. An analogy is often used here with caution. A long cable looks one-dimensional from a distance. Only when examined closely does its circular cross-section become apparent. Similarly, space might have additional dimensions that only become apparent at extremely small scales. It is important not to take this analogy too literally. The mathematics of compactified dimensions is highly sophisticated and involves complex geometric structures. What matters conceptually is that space-time in string theory is richer than the three-dimensional space of experience. These extra dimensions are not optional. They are required for mathematical consistency. Without them, the theory develops internal contradictions. This is both a strength and a weakness. It provides a clear structure, but it also places string theory far beyond direct experimental test. Spacetime, in this framework, is not fundamentally quantized in the same way as in loop quantum gravity. Instead, the smoothness of spacetime emerges because the fundamental objects interacting within it are extended. The strings smear interactions over small distances, preventing the formation of singularities in the same way point particles would. In this sense, string theory addresses the problem of quantum spacetime indirectly. It does not begin by discretizing geometry. It modifies the behavior of matter and forces so that spacetime remains well behaved even at very small scales. This leads to a different intuition. Rather than spacetime breaking into discrete chunks, spacetime remains continuous, but the physics occurring within it is softened at short distances. Singularities are avoided not by quantizing geometry itself, but by changing what interacts within that geometry. This distinction matters when comparing approaches. Loop quantum gravity predicts discrete geometric quantities. String theory predicts smooth geometry with new degrees of freedom that prevent breakdowns. Both approaches aim to resolve the same problem, but they do so using different assumptions. String theory also introduces a powerful idea known as duality. Different physical descriptions which appear unrelated can turn out to be mathematically equivalent. A theory defined in one spacetime geometry may describe the same physics as a theory defined in a very different geometry. One important example of this idea connects gravity in a higher dimensional spacetime to a quantum field theory defined on its boundary. This suggests that spacetime geometry might emerge from more fundamental non-geometric degrees of freedom. Distance and volume could be derived quantities rather than primitives. This has led some physicists to suggest that spacetime itself is not fundamental in string theory. Instead, it arises from patterns of interaction within a deeper framework. In that view, asking when spacetime becomes quantum may be the wrong question. Spacetime may be an effective concept that only appears under certain conditions. Despite its mathematical richness, string theory faces serious challenges. The most significant is testability. The characteristic scales at which string effects become important are expected to be close to the Planck scale. This places them far beyond the reach of current or foreseeable experiments. No direct experimental evidence supports the existence of strings or extra dimensions. There's also the issue of uniqueness. String theory does not produce a single, clearly defined universe. Instead, it allows an enormous number of possible solutions, each corresponding to different physical constants and properties. Explaining why the universe has the particular structure observed becomes difficult. Supporters argue that this flexibility may be a feature rather than a flaw. It may reflect the true complexity of fundamental physics. Critics argue that without predictive power, the theory risks becoming disconnected from observation. These debates are ongoing and active. They are part of what makes string theory both influential and controversial. What matters for the question of quantum spacetime is not whether string theory is correct, but what it demonstrates. It shows that there are multiple coherent ways to approach the problem. One can attempt to quantize geometry directly, or one can modify the underlying constituents of matter so that geometry remains smooth. String theory occupies the second path. It offers a vision in which spacetime does not fragment or fluctuate wildly at small scales. Instead, the violent infinities that plague point particle theories are avoided because interactions are fundamentally extended. Geometry remains continuous, but its meaning is tied to deeper structures. This broadens the theoretical landscape significantly. It shows that quantum spacetime does not have a single obvious form. Different assumptions lead to different pictures, each internally consistent and grounded in established physics. In that sense, string theory complements rather than replaces other approaches. It provides a contrasting answer to the same underlying question. How can quantum mechanics and gravity coexist without contradiction? Whether spacetime becomes quantum through discreteness, emergence, or extended interactions remains unresolved. String theory shows that smooth spacetime might survive at all scales, not because it is fundamental, but because the objects within it are. This perspective does not settle the issue, it deepens it. By offering a radically different route to quantum spacetime, string theory forces the question to be asked more carefully. What exactly is meant by spacetime becoming quantum? Is it geometry that changes, or the entities that give geometry meaning? These questions remain open. What is clear is that string theory has reshaped how physicists think about spacetime, scale, and unification. Even if it turns out not to describe nature directly, its influence on the search for quantum spacetime is undeniable. It stands as a reminder that the path from smooth spacetime to quantum reality may not be singular, and that the correct description may lie deeper than geometry itself. One of the most far-reaching ideas to emerge from attempts to understand quantum spacetime is that spacetime itself may not be fundamental. Instead of being a basic ingredient of reality, it may arise from deeper processes, much as other familiar physical quantities do. This proposal shifts the problem in a subtle but important way. Rather than asking how to quantize spacetime, it asks whether spacetime needs to be quantized at all. It asks whether smooth geometry is something that exists at the most basic level, or whether it appears only when many underlying degrees of freedom are considered together. Physics already contains several examples of this kind of emergence. Temperature feels like a basic property of matter. Objects are hot or cold. Temperature can be measured precisely and behaves predictably. Yet temperature does not exist at the level of individual particles. A single atom does not have a temperature. Temperature emerges only when many particles interact and exchange energy. It is a collective property, not a fundamental one. The same is true of pressure. Pressure describes how strongly a gas pushes on the walls of a container. It can be calculated, measured, and used reliably in engineering. But pressure is not a property of a single molecule. It arises from countless collisions averaged over time. Fluids provide another useful comparison. Water appears smooth and continuous when flowing through a river. The equations of fluid dynamics describe this motion accurately at large scales. At smaller scales, water is composed of discrete molecules moving chaotically. The smooth flow is real, but it is not fundamental. It emerges from underlying microscopic behavior. These examples show that a description can be accurate and indispensable without being fundamental. Emergence does not mean illusion. It means scale dependence. Applied to spacetime, this suggests that distance, duration, and geometry may play the same role as temperature or pressure. They may describe collective behavior rather than microscopic structure. At large scales, spacetime behaves smoothly and predictably. At small scales, the concept of spacetime may dissolve into something more basic. This perspective reframes earlier difficulties. The incompatibility between quantum mechanics and general relativity may arise not because spacetime needs to be quantized in the usual sense, but because spacetime itself is not the right object to quantize. If spacetime is emergent, then quantum mechanics and gravity may be operating at different descriptive levels. Quantum mechanics would govern the fundamental degrees of freedom. spacetime geometry would describe their large-scale organization. This idea appears in several modern approaches to theoretical physics, most notably in work related to holography. The holographic principle proposes that the information contained within a region of space can be described entirely by data on its boundary. The name comes from an analogy with holograms, where a two-dimensional surface encodes a three-dimensional image. In physics, the idea suggests that volume and geometry may not be primary. They may arise from more fundamental lower-dimensional descriptions. A concrete realization of this idea was proposed by Juan Maldacena in the late 1990s. He discovered a precise mathematical relationship between two very different kinds of theories. One describes gravity in a higher dimensional spacetime. The other describes a quantum field theory without gravity in a lower dimensional setting. Remarkably, these two descriptions encode the same physics. Calculations performed in one can be translated into calculations in the other. Spacetime geometry on one side corresponds to quantum interactions on the other. The significance of this result lies not in the technical details, but in what it implies conceptually. It suggests that spacetime geometry can emerge from quantum degrees of freedom that do not themselves live in spacetime in the usual sense. Distance, curvature, and gravity become derived concepts rather than starting points. In this framework, spacetime is not quantized directly. Instead, quantum mechanics governs a more fundamental system, and spacetime appears when that system is described at large scales or low energies. This changes how the question of quantum spacetime is posed. If spacetime is emergent, then asking when spacetime becomes quantum may be misleading. Spacetime may never be quantum in the same way particles are. Instead, the underlying system is quantum and spacetime inherits properties from it. This would explain several puzzling features encountered earlier. The appearance of a minimum length and time scale may reflect limits on how spacetime emerges, not discrete building blocks of space and time. Singularities may signal the breakdown of the emergent description rather than physical infinities. Quantum foam may reflect uncertainty in the underlying degrees of freedom rather than literal fluctuations of geometry. Emergence also helps explain why spacetime behaves so classically, across such a wide range of scales. Just as temperature behaves smoothly, even though it arises from quantum particles, spacetime geometry could behave smoothly, even if it arises from fundamentally quantum processes. This does not mean that spacetime is less real. Emergent phenomena are real. Pressure can rupture containers. Temperature drives engines. Fluid flow shapes landscapes. Emergence describes how reality is organized, not whether it exists. However, emergent descriptions have limits. They work only when the conditions that support them are met. When those conditions fail, the description must be replaced. In the case of spacetime, those conditions may involve scale, energy, and organization of underlying degrees of freedom. At everyday and astronomical scales, spacetime emerges robustly. At extreme densities or small scales, it may fail. This view also clarifies why no experiment has yet detected spacetime discreteness or quantum fluctuations directly. If spacetime is emergent, then probing its underlying structure would require accessing the fundamental degrees of freedom from which it arises. These may be far removed from geometric concepts and inaccessible to current technology. Importantly, emergence does not eliminate the need for precise theory. It demands it. One must specify what spacetime emerges from, how it emerges, and under what conditions the emergent description applies. These questions are technically demanding and remain open. Different approaches propose different answers. Some suggest spacetime emerges from quantum entanglement patterns. Others propose more abstract mathematical structures. Some retain geometry at a fundamental level, others do not. What unites these approaches is a shift in emphasis. Spacetime is no longer assumed to be the stage on which physics happens. It becomes part of the outcome. This shift has philosophical implications as well. If spacetime is emergent, then familiar notions such as locality and simultaneity may also be emergent. The idea that events occur at definite places and times may apply only within the emergent regime. At deeper levels, relationships may not map cleanly onto spatial separation or temporal order. This does not undermine causality or physical law. It reframes them. Causes and effects may still be linked, but not always in ways that correspond to classical spacetime intuition. The emergence perspective also encourages caution. It warns against assuming that concepts successful at one scale must apply universally. It suggests that the breakdown of smooth spacetime at small scales is not a failure of physics, but a sign that the wrong variables are being used. Seen this way, the central question evolves. Instead of asking when spacetime becomes quantum, the focus shifts to when spacetime stops being the right language altogether. This reframing does not provide final answers. It changes the terrain on which answers are sought. It opens the possibility that spacetime, like temperature or pressure, is a powerful but limited concept. That possibility reshapes how the problem of quantum gravity is approached. It suggests that reconciliation may not come from forcing two incompatible frameworks together, but from recognizing that they describe different layers of reality. At large scales, spacetime geometry describes the organization of matter and energy. At small scales, quantum rules govern the underlying constituents. The challenge is not to choose one description over the other, but to understand how they connect. Emergent spacetime offers one coherent way to think about that connection. It preserves the success of general relativity without insisting on its universality. It respects quantum mechanics without demanding that spacetime behave like a particle. Whether this picture is correct remains unknown. What it provides is a powerful conceptual lens. It allows the question of quantum spacetime to be asked with greater precision and fewer assumptions. Spacetime may not become quantum in the way matter does. It may become irrelevant, replaced by deeper structures that only resemble space and time when viewed from far enough away. That possibility does not diminish the reality of spacetime. It places it in context. Understanding that context prepares the ground for broader reflection. If spacetime is emergent, then questions about meaning, causality, and reality itself must be reconsidered carefully, without abandoning the rigor that physics demands. Ideas about quantum spacetime are ambitious, mathematically rich, and often far removed from direct observation. This raises an unavoidable question. If spacetime becomes quantum only at extreme scales, what can experiments actually test, and where do the limits of observation lie? The difficulty begins with scale. Quantum spacetime effects are expected to become significant near the Planck length and Planck time. These scales are enormously smaller than anything that can be probed directly. Even the most energetic particle accelerators fall many orders of magnitude short of the energies required to resolve such distances. This is not a temporary limitation. It reflects fundamental constraints set by gravity and quantum mechanics themselves. As a result, no experiment can directly look at spacetime at the scale where quantum effects are expected to dominate. There is no microscope powerful enough to see it, and no detector that can isolate such short intervals without disturbing the system beyond recognition. This does not mean that experiment has nothing to say. It means that tests must be indirect. Physics often advances this way. Atoms were accepted long before individual atoms could be imaged. Neutrinos were proposed decades before they were detected. In each case, theory made predictions about observable consequences at accessible scales. The same approach applies here. One promising observational arena involves gravity under extreme conditions. Gravitational waves provide a particularly important example. These waves are distortions in spacetime itself, produced by accelerating masses such as merging black holes and neutron stars. The detection of gravitational waves by the LIGO collaboration confirmed a key prediction of general relativity. The observed signals matched theoretical models with remarkable precision. This success reinforces confidence in the classical description of spacetime at macroscopic scales. At the same time, gravitational wave observations push gravity into regimes that were previously inaccessible. Black hole mergers involve enormous energies and strong spacetime curvature. By comparing observed signals to theoretical predictions, physicists can test whether general relativity continues to hold under these conditions. So far, it does. No deviations from classical predictions have been observed. This places important constraints on proposed theories of quantum gravity. Any viable theory must reproduce the observed behavior of gravitational waves to high accuracy. Exotic effects that would noticeably alter these signals are ruled out. This illustrates a key point. Even without direct access to Planck-scale physics, experiments can still eliminate large classes of speculative ideas. The absence of observed anomalies is itself a form of evidence. Another potential testing ground lies in cosmology. The large-scale structure of the universe carries imprints of its early history. Tiny variations in the distribution of matter and radiation reflect conditions in the very early universe. Some theories of quantum spacetime predict subtle modifications to these patterns. Measurements of the cosmic microwave background radiation, for example, provide a snapshot of the universe when it was only hundreds of thousands of years old. These measurements are extraordinarily precise. They constrain how space expanded, how matter clustered, and how energy was distributed. Any theory proposing radical departures from classical spacetime must be consistent with these observations. So far, the data strongly support the standard cosmological model, based on general relativity and quantum field theory, applied to matter, not spacetime itself. This again narrows the field. Quantum spacetime effects, if they exist, must be subtle enough to leave the early universe largely unchanged at observable scales. Laboratory experiments also play a role, though a limited one. Precision measurements of quantum systems can test whether spacetime behaves classically down to very small scales. Experiments involving atomic clocks, interferometers, and quantum coherence probe how well quantum mechanics and relativity coexist in everyday conditions. These experiments have confirmed both theories with increasing accuracy. Time dilation has been measured over height differences of less than a meter. Quantum superpositions have been maintained over macroscopic distances. No breakdown of classical spacetime has been observed in these regimes. This places strong lower bounds on where quantum spacetime effects could appear. If spacetime has a granular or fluctuating structure, it must be hidden well below the scales currently accessible. It is also important to recognize what experiments cannot test. Many proposed effects of quantum spacetime are intrinsically unobservable with present or foreseeable technology. For example, tiny fluctuations in geometry at the Planck scale would average out over any realistic measurement. Their direct detection would require sensitivity far beyond physical limits imposed by noise, energy, and gravity itself. This is not a failure of ingenuity. It is a consequence of how nature behaves. there is also a conceptual limit. Some questions may not correspond to observable distinctions. If two descriptions of quantum spacetime produce identical predictions at all accessible scales, no experiment can distinguish between them. In that case, the difference may be one of interpretation rather than physics. This situation is not unique. In quantum mechanics, different mathematical formulations can describe the same observable phenomena. Physics progresses by focusing on what can be tested, not by insisting that every theoretical detail must be experimentally resolved. Recognizing these limits is part of scientific maturity. The role of experiment in this context is therefore selective. It does not provide direct images of quantum spacetime. It constrains theories by demanding consistency with everything that is already known. It rules out ideas that conflict with observation, and it leaves open those that do not. This balance is delicate. On one hand, theory must remain connected to experiment. On the other, the absence of direct tests does not automatically disqualify theoretical work, especially when it addresses deep inconsistencies in existing frameworks. The history of physics contains many examples where theory ran ahead of experiment for long periods. The key requirement is that theories remain grounded in established principles and produce clear, testable consequences in principle, even if not immediately. This is where caution is essential. Claims that quantum spacetime effects are just around the corner should be treated skeptically. At the same time, dismissing all such work as unscientific ignores how foundational progress is made. Experiments set the boundaries. Theory explores the interior. Gravitational wave astronomy, precision quantum measurement, and cosmological observation together define a broad experimental framework. Within that framework, spacetime behaves classically to a very high degree of accuracy. Any quantum description must reproduce this behavior. Beyond that framework lies uncertainty, not because science has failed, but because the questions being asked push against the limits of what can be measured. Understanding what experiments can and cannot test helps clarify the status of quantum spacetime. It is not an idea floating free of reality. It is constrained, shaped, and guided by observation, even when it ventures far beyond current reach. This grounding matters. It prevents speculation from drifting into fantasy. It ensures that discussions of quantum spacetime remain anchored to physical reality, even when that reality cannot yet be fully explored. With thus constraints in mind, the remaining task is to assess what is known, what is unknown, and what may remain unknowable. That distinction defines the true frontier. At this point, the shape of the boundary becomes clearer. Physics has carried its most successful theories as far as they can reliably go, and beyond that edge, the landscape changes. Not into speculation without discipline, but into questions that current tools cannot yet answer. General relativity provides a precise and tested description of spacetime as a smooth geometric structure. It explains gravity, cosmic expansion, black holes, and gravitational waves with extraordinary accuracy. Within the regimes where it has been tested, it shows no sign of failure. Its equations remain well behaved, its predictions consistent with observation. Quantum mechanics is equally successful. It describes matter, energy, and fields at small scales with unmatched precision. Its probabilistic framework underpins modern technology and experimental physics. No alternative theory has ever surpassed its predictive power in its domain. Each theory, taken on its own terms, works. The boundary appears when both are applied at once. When gravity is weak and scales are large, quantum effects fade into the background. When quantum effects dominate and gravity is negligible, spacetime can be treated as fixed. The difficulty arises in the narrow overlap where gravity is strong and quantum behavior cannot be ignored. That overlap defines the frontier. At present, physics does not possess a complete, experimentally confirmed theory that describes spacetime under those conditions. Attempts exist. Some treat geometry as quantized. Some treat spacetime as emergent. Some modify the nature of fundamental objects. All are mathematically sophisticated. None have been verified. This is where current theories stop being sufficient. They do not stop working abruptly. They stop answering certain questions. General relativity predicts singularities, but does not describe what happens at them. Quantum mechanics predicts fluctuations, but does not specify how spacetime responds. Together, they point to a regime where familiar concepts lose meaning without being replaced by agreed alternatives. That regime is not vague. It is sharply constrained by known physics. The Planck scale marks where quantum uncertainty, gravitational interaction, and spacetime structure converge. Below that scale, standard notions of distance and duration cease to have operational meaning. Above it, classical spacetime works extremely well. This is not ignorance in the ordinary sense. It is a structural boundary. Within physics, it is important to distinguish between what is unknown and what may be unknowable. Unknown questions are those that current theories cannot answer, but future theories might. For example, whether spacetime is fundamentally discrete or emergent is unknown. Whether singularities are resolved by quantum effects is unknown. Whether spacetime geometry arises from entanglement or other structures is unknown. These questions are active areas of research. Unknowable questions are different. They concern distinctions that no possible experiment could resolve, even in principle. If two theories make identical predictions at all accessible scales, then no observation can choose between them. In that case, the difference may not correspond to physical reality. Physics has encountered this before. Different formulations of quantum mechanics describe the same observable phenomena. The choice between them often reflects preference rather than experiment. Recognizing this does not weaken physics. It clarifies its scope. Some aspects of quantum spacetime may fall into this category. Certain details of microscopic structure may never produce observable consequences. If so, physics may describe limits rather than mechanisms. This does not imply that inquiry should stop. It implies that expectations should be realistic. The research culture surrounding quantum gravity reflects this awareness. Physicists working in the field are careful about claims. Progress is measured in consistency, mathematical coherence, and connection to known physics, not in dramatic predictions. Work continues across many directions. Researchers explore loop-based approaches, string-based frameworks, holographic models, and numerical simulations of quantum geometry. They refine mathematical tools, test internal consistency, and search for indirect observational signatures. This effort is distributed across universities, institutes, and collaborations worldwide. It is incremental rather than revolutionary. Advances are often technical and slow. This pace is not a sign of stagnation. It reflects the depth of the problem. There is also a recognition that new ideas may require new ways of thinking. Many foundational shifts in physics came not from extending existing theories, but from re-examining assumptions. The concept of emergent spacetime is one example of this. It challenges the assumption that space and time must be fundamental. At the same time, restraint is essential. History shows that radical ideas must earn their place through consistency and evidence. Elegant mathematics alone is not enough. Neither is philosophical appeal. The boundary of current physics is therefore not a wall, it is a transition zone. On one side lie theories that have been tested and confirmed repeatedly. On the other lie frameworks that aim to extend those theories into regimes not yet accessible. The boundary is defined by scale, by measurement, and by operational meaning. This boundary also serves a practical role. It prevents overreach. It reminds physics where confidence ends and conjecture begins. It keeps speculation anchored to what is known. At the same time, it provides direction. By identifying precisely where current descriptions fail, it highlights where new insight is needed. Singularities, Planck scale limits, and the incompatibility of quantum mechanics with dynamic spacetime are not vague mysteries. They are specific failures of existing frameworks. That specificity matters. It allows progress to be judged objectively. A new theory must reproduce classical spacetime at large scales. It must respect quantum principles where they are known to apply. It must resolve rather than hide the known breakdowns. Until such a theory is confirmed, the boundary remains. This does not diminish what physics has achieved. On the contrary, it reflects how far understanding has already been pushed. Few sciences can define their limits so precisely. The boundary of current physics marks not ignorance, but honesty. It distinguishes what can be said with confidence from what remains open. It separates established knowledge from active investigation. Recognizing that boundary prepares the ground for synthesis, it allows the central question to be revisited with clarity rather than expectation. What is known, what is unknown, and what may never be resolved can now be placed in proper context. From that position, the discussion can move toward integration rather than expansion. The aim is no longer to add more theories, but to understand how existing insights fit together, where they overlap, and where they must eventually give way. That shift signals the approach of a different kind of conclusion. Not one that resolves the problem, but one that places it within a coherent picture of what physics can and cannot say. After tracing the ideas, limits, and proposals that surround quantum spacetime, the original question can now be faced directly. Does spacetime truly become quantum, or is that way of phrasing the problem misleading? The honest answer is conditional. It depends on what is meant by spacetime, what is meant by quantum, and at what scale the question is being argued. At large scales, spacetime behaves classically. Distances are well defined. Time orders events reliably. Geometry responds smoothly to mass and energy. General relativity describes this behavior with exceptional accuracy, and no experiment has contradicted it. In this regime, spacetime does not appear quantum in any operational sense. At small scales, matter and energy behave quantum mechanically. Probabilities replace certainties. Measurements disturb what is measured. Discreteness and uncertainty are unavoidable. Quantum mechanics governs this domain, and its predictions are confirmed repeatedly. In this regime, spacetime is usually treated as a background rather than an object of study. The tension arises in the overlap between these regimes. When both gravity and quantum effects are strong, neither classical spacetime nor standard quantum mechanics can be applied without qualification. This is where the question of quantum spacetime becomes unavoidable. Different theoretical approaches answer the question in different ways. In loop quantum gravity, spacetime is quantum at all scales. Geometry itself is quantized. Areas and volumes take discrete values. Smooth spacetime is an emergent approximation that appears only when many quantum geometric elements are averaged together. In this view, spacetime does not become quantum at a particular point. It is quantum by nature, and classical behavior is a large-scale illusion. In string theory, spacetime remains smooth, but the objects within it are fundamentally quantum and extended. Singularities are avoided not because geometry is discrete, but because interactions are softened at short distances. Spacetime does not fragment. Instead, its role becomes secondary to deeper structures. In this view, spacetime may not need to become quantum at all. It may remain classical while being derived from quantum ingredients. In emergent spacetime approaches, spacetime is not fundamental in either sense. It arises from more basic quantum degrees of freedom that do not resemble space or time. Geometry appears only when those degrees of freedom organize in certain ways. In this view, spacetime never becomes quantum, because it was never fundamental to begin with. The quantum behavior lies beneath it. These answers are not merely different opinions, they reflect different assumptions about what spacetime is. If spacetime is treated as a physical field, like electromagnetism, then it makes sense to ask how it behaves under quantization. If spacetime is treated as an emergent description, then quantizing it directly may be the wrong approach. If spacetime is treated as a smooth arena softened by extended interactions, then discreteness may never appear. Each perspective is internally consistent. None is experimentally confirmed. What unites them is a shared conclusion. The smooth spacetime of experience is not fundamental across all scales. Whether through quantization, emergence, or modification, the classical picture fails when pushed far enough. Scale is the key variable. At human, planetary, and even galactic scales, spacetime behaves classically. At atomic scales, spacetime provides a stable background while quantum behavior dominates matter. At Planck scale conditions, the separation between spacetime and quantum behavior breaks down. This does not imply a sharp boundary in space or time. There is no location in the universe where spacetime suddenly changes character. There is no moment at which geometry flips from classical to quantum. The transition is scale-dependent, not spatially localized. The same region of space can be well described by classical geometry at one resolution and poorly described at another. Just as temperature ceases to be meaningful when only a few particles are involved, space-time geometry may cease to be meaningful when only a few underlying degrees of freedom are involved. This reframes the central question. Instead of asking when space-time becomes quantum, a more precise question emerges. At what scale do the concepts of distance, duration, and geometry stop being reliable descriptions of physical reality? That question has a clearer answer. Current theory strongly suggests that below the Planck scale, classical spacetime concepts lose operational meaning. Distances cannot be defined without disrupting geometry. Time intervals cannot be resolved without invoking energies that destroy the notion of duration. Causality becomes difficult to define using familiar structures. Above that scale, spacetime behaves smoothly and predictably. This does not require spacetime to be literally quantized in the way energy levels are. It requires only that classical spacetime is an effective description, valid within a certain range. From this perspective, asking whether spacetime truly becomes quantum may be like asking whether temperature becomes quantum at small scales. The answer depends on context. Temperature remains a useful concept at large scales and fails at small ones. Its failure does not mean it was never real. It means it was never fundamental. Spacetime may occupy a similar position. This view also clarifies why progress has been slow. The question being asked lies at the boundary of what can be defined operationally. It concerns entities that may not admit direct measurement or clear distinction. It requires new conceptual frameworks, not just new calculations. That does not make the question meaningless. It makes it subtle. Physics advances by refining questions as much as by answering them. The journey from smooth spacetime to quantum descriptions has already revealed where existing concepts hold and where they fail. That alone is a significant achievement. So does spacetime truly become quantum? If the question means whether spacetime must be treated using quantum principles at sufficiently small scales, the answer is likely yes. Classical geometry cannot be extended indefinitely. If the question means whether spacetime is made of discrete quantum units, the answer is unknown and theory-dependent. If the question means whether spacetime itself is a quantum object in the same sense as particles, the answer may be no. The most robust conclusion is this: spacetime, as currently understood, is not the final layer of physical description. Its smoothness, continuity, and stability are properties that apply within a certain range of scale. Outside that range, different concepts are required. This does not diminish the reality of spacetime, it places it in context. Spacetime works where it is used. It fails where it should not be used. That is not a flaw. It is how effective descriptions behave. The question of quantum spacetime therefore resolves into something quieter but more precise. Not when spacetime becomes quantum, but when spacetime stops being the right language. That recognition integrates everything that has come before. It preserves the successes of general relativity. It respects the necessity of quantum mechanics. It acknowledges the limits of experiment. It avoids forcing incompatible ideas together. From this position, the discussion naturally shifts away from debate and toward reflection. Not reflection in the sense of speculation, but in the sense of understanding what physics can reasonably claim. Spacetime may or may not be quantum in a fundamental sense. What is clear is that its familiar form is scale-bound. Knowing that is not the end of the story. It is the condition for asking the next question properly. Living in a universe with limits is not a failure of understanding. It is the condition under which understanding becomes possible. At human scales, the universe behaves in ways that are stable, predictable, and deeply familiar. Distances can be measured, time can be tracked, objects occupy places, events follow one another in reliable order. Smooth spacetime is not an approximation in daily life. It is the structure through which reality is experienced. That matters. The fact that spacetime may not be fundamental does not make it provisional or disposable. Temperature is not fundamental, yet it governs weather, biology, and chemistry. Pressure is not fundamental, yet it shapes stars and atmospheres. Smooth spacetime plays the same role. It is the correct description at the scale where human life, planetary motion, and cosmic evolution unfold. Physics does not aim to replace effective descriptions with deeper ones indiscriminately. It aims to use the right description at the right scale. Recognizing limits sharpens that aim. The search for quantum spacetime reveals that even our most successful concepts have domains of validity. Spacetime geometry works remarkably well across an enormous range of scales. It fails only when pushed into regimes where measurement itself becomes problematic. That failure is not an embarrassment. It is a guide. It tells us where not to extend familiar ideas. This perspective carries an important lesson about scientific humility. Physics progresses not by assuming that every concept must apply universally, but by identifying where concepts stop working. Knowing the boundary of a theory is as important as knowing its predictions. Smooth spacetime still matters because it is the language through which gravity, motion, and causality are understood in the world that can be observed. No proposed theory of quantum gravity replaces that fact. Any deeper theory must recover smooth spacetime as an emergent description, or it fails immediately. This places limits in their proper role. Limits are not barriers to meaning, they define it. There is a tendency, especially when discussing fundamental physics, to treat deeper explanations as more real than effective ones. This hierarchy can be misleading. Reality is not organized by depth alone. It is organized by relevance. The smoothness of spacetime is relevant to building bridges, navigating spacecraft, predicting eclipses, and understanding cosmic expansion. Its possible breakdown at unreachable scales does not weaken its authority where it applies. At the same time, the existence of limits prevents overconfidence. The idea that spacetime might cease to be meaningful at extremely small scales forces restraint. It discourages the assumption that intuition built from everyday experience can be applied universally. It reminds us that concepts such as distance and duration are tools, not absolutes. This restraint is not pessimism, it is precision. Scientific humility does not mean retreating into vagueness. It means stating clearly what is known, what is unknown, and what may never be expressible in familiar terms. The distinction between unknown and unknowable matters here. Some questions remain open because better theories or experiments may answer them. Others may be unanswerable because they ask for distinctions that have no operational meaning. Accepting this does not diminish inquiry, it refines it. Living in a universe with limits also shapes how uncertainty is held. Uncertainty in physics is often misunderstood as ignorance or failure. In reality, it is frequently the product of clarity. When physics reaches a point where questions can be posed but not resolved within existing frameworks, uncertainty is the honest response. This kind of uncertainty is calm. It does not demand resolution at all costs. It does not invent structure where none is supported. It recognizes that understanding is layered, and that some layers may not admit the same kinds of explanation as others. This calm uncertainty is visible throughout the study of quantum spacetime. Theories are proposed carefully, claims are constrained. Speculation is bounded by consistency with what is already known. Progress is measured in coherence rather than spectacle. That attitude reflects a mature science. It also has philosophical consequences. If spacetime is emergent, then the universe is not obliged to align with human intuitions about continuity and locality. If spacetime has limits, then reality is under no obligation to be fully describable in the language evolved for survival at moderate scales. This is not unsettling once it is understood properly. It is liberating. It means that physics is not failing when it encounters conceptual limits. It is succeeding in identifying them. It means that not every question needs an answer in order for understanding to deepen. Smooth spacetime remains the environment in which life unfolds. It is the arena in which meaning, causality, and experience take shape. That does not change if spacetime emerges from something deeper. Emergence does not erase reality. It explains it. The universe does not become less real when its foundations are questioned. It becomes more precisely understood. Living with limits, therefore, does not require resignation. It requires adjustment. It requires accepting that some aspects of reality are scale-dependent, and that descriptions valid at one scale may fail at another without contradiction. This acceptance has always accompanied major advances in physics. Absolute space gave way to relativity. Determinism gave way to probability. Each shift involved letting go of assumptions that once seemed unavoidable. The possible non-fundamental nature of spacetime belongs to that lineage. It is not an anomaly, it is a continuation. What remains constant is the role of careful reasoning, empirical grounding, and conceptual restraint. These principles do not dissolve at the limits of knowledge, they become more important. In the end, living in a universe with limits is not a philosophical compromise. It is a scientific achievement. It reflects the ability to map where understanding holds and where it must pause. That pause is not emptiness, it is space for reflection. Understanding that spacetime works where it works, fails where it should fail, and may not apply everywhere is not a loss. It is clarity without illusion. From that position, the universe appears neither fully transparent nor fundamentally obscure. It appears structured, layered, and conditional. That is enough. The question of quantum spacetime does not demand certainty to be meaningful. It demands honesty about scale, language, and reach. Within those bounds, understanding remains solid, even when answers remain incomplete. Living in such a universe is not a problem to be solved. It is the context in which knowledge exists. Asking when spacetime becomes quantum turns out to be less about finding a hidden boundary, and more about understanding how description depends on scale. What is known is solid. At the scales where measurement is possible, spacetime behaves smoothly and predictably. General relativity describes gravity with extraordinary accuracy. Quantum mechanics governs matter and energy with unmatched precision. Each theory works exactly where it should. What is unknown lies where those descriptions overlap. At extremely small scales, the concepts of distance and duration begin to lose clear meaning. Whether spacetime is quantized, emergent, or derived from deeper structures remains unresolved. Multiple consistent frameworks exist, but none has yet been confirmed. That uncertainty is not a failure. It is a signal that physics has reached the edge of what current concepts can express. What this question ultimately reveals is restraint. It shows that nature does not guarantee simple answers at every scale, and that understanding does not require finality to be real. Smooth spacetime still matters because it is the right language for the world that can be experienced. Its possible limits do not weaken it. They place it in context. Seen this way, quantum spacetime is less a destination than a perspective. It reminds us that reality is layered, that descriptions are conditional, and that curiosity does not require closure. Sometimes understanding means knowing where to stop, and sometimes that is enough.